All right, so picking back up where we left off, we were looking at our linear kinematic equations, and then we were just going to update all of our linear values with our new angular values in terms of radians. And again, everything works the exact same way. So for this first one, when we have no acceleration, our omega would be equal to our delta theta over time. For our second one, we would have omega final is equal to omega initial plus alpha times time. Then we would have a delta theta is equal to an omega naught t plus 1/2 alpha t squared. And then our omega final squared is equal to omega initial squared plus 2 alpha delta theta. All right, so here ends one spot in the discussion, and I'm going to kind of shift gears almost completely to talk about centripetal force and centripetal acceleration. So this first half here is just looking at a little intro to our angular kinematics. We got a couple of new equations. We have our old kinematic equations that are now updated to our angular values. Again, the only difference is linear is looking at meters, where angular is looking at radians. Okay. Now, for this next portion, I want to look at something that is moving moving in a circle. Okay, I'm going to imagine some little object sitting on top of a rotating disc. So I'm looking like straight on at it instead of aerial view now, but I have my little object. It would move in a circle on this little rotating disc here. So this is a disc. This is the object on the disc is spinning, so the object is spinning, okay? I'm gonna draw a free body diagram where I would have a force of gravity for the object pointed downward, and then I would have a normal force pointed upward, okay? Now, but this object is remaining on the disc as the disc turns, which means that I need to have some friction in this disc in order to keep this object from sliding out, because it would slide away from the disc if I didn't have a force of friction holding it inward, okay? So if my center of my circle is over here, so I'm rotating around a point right here, so let's say that's fixed into the ground, you can call it a little pin or something, then I would have a force of friction pointed this way towards that center, because that ball or that object or whatever this is would want to slide outward. Okay, now notice this force of friction is pointed towards the center, and that's where you get the name centripetal force. Centripetal just means center seeking. So that force is towards the center, and that force towards the center in any scenario, we're going to talk about a couple of different ones, but in any scenario, that force towards the center is what's going to keep the object in the circular motion, okay? So I'm going to kind of take a little pause here, scroll down, and we'll scroll back up to keep analyzing that scenario. So if I look at that object now from an overhead view, so overhead view for my little object that we drew before, okay? So that object is going to move in a circle, and for this scenario, let's say it's moving counterclockwise in a circle, okay? So again, just like we did above, no matter where I look at it, it would have a linear velocity that is tangent to the circle. So linear velocity here, tangent to the circle. I'm only going to draw 4 of them, but I would really have just about an infinite amount of these tangent lines that create that smooth surface of the edge of a circle, okay? Now, all of the speeds are going to be the same. So I'm going to say that this object is moving at a constant speed around the circle. But what changes here is the direction. All of these velocities are in a different direction. So if I'm thinking about looking at this object at all of these different spots, and every single spot it would be moving in a different direction. And so if the direction changes, then the velocity changes. Remember, velocity has our direction and our magnitude. I have to have both of them. So in order for this velocity to change, I need an acceleration. If you remember, accelerations are caused by unbalanced forces. So if this scenario is the same as this scenario, then it would be this force of friction pointed towards the center that would be causing an acceleration. This would be the force pulling it in towards the center of the circle, keeping it in the circular motion, therefore changing the direction of the velocity. So that force is pointed towards the center, and our net force and our acceleration always point in the same direction. So that means that no matter where I am, I have this acceleration pointed towards the center. So this acceleration pointed towards the center because I have that force pointed towards the center. I'm going to label that AC for centripetal acceleration. So that acceleration is pointed towards the center because it comes from the centripetal force, which is also pointed towards the center. Okay. Now, this acceleration, this centripetal acceleration, gets its own equation. I'm just going to tell you what that is. I'm going to go ahead and throw it out there that it's v squared over r. Up until this point, you've probably discovered that I derive every equation, and I will throw in a different video of me deriving this equation. However, it's kind of lengthy, and I've found over the years that it does more harm than good, meaning it confuses more people than it helps. So if you want to see how I derive this centripetal acceleration, watch the other video. I'll make it sometime this week and throw it up into the notes from this week, okay? But if not, if you just want to know the equation to know it, then this is what we got. So we have our centripetal acceleration, which is an acceleration that is changing this linear velocity, this velocity that's tangent to the circle. So this centripetal acceleration is a linear acceleration. It's changing a linear velocity, okay? And the only job of this centripetal acceleration is to change the direction. It is not going to make the object speed up or slow down. So where it comes into play then is when I go to sum my forces in my y direction, so the sum of my forces in the y, that's going to be equal to 0 because everything is balanced. But in the x direction, I have this centripetal force and I need this centripetal acceleration. I need this acceleration to change the direction of my motion. So we would get Fn minus Fg is equal to 0, or Fn is equal to Fg. So then in the x direction, my force of friction is the one that is causing this centripetal acceleration. So I could say that my force of friction is equal to mv squared over r, okay? So this centripetal force causes this centripetal acceleration, okay? But centripetal force is not its own brand new type of force. All of the forces can act as a centripetal force. So in this case, the force of friction is what's keeping the object in a circle. So the force of friction is what's acting as the centripetal force in this case. So I don't ever want to label this force of friction Fc because it is a force of friction. It's just acting as a centripetal force. It's acting as a force that keeps our object in a circle. Okay. So for the next example, I want to think of a Ferris wheel because something very specific happens on a Ferris wheel or on a roller coaster or sometimes in a elevator, okay? And that's where at certain parts of the ride, you feel lighter, and at certain parts, you feel heavier. So if I think like a roller coaster, at the top of a hill, you feel light. At the bottom of a hill, you feel heavy. Now, that's cool. We all know that happens because we feel that, except for your force of gravity does not change because your mass didn't change and the planet you're on, so your acceleration did not change, okay? What changes here is your normal force. So your normal force is your perceived weight. You walk around all day long feeling subconsciously how much the ground has to push up on you to keep you from falling down, okay? So the normal force is what you feel. So if you feel lighter at the top, then my normal force at the top must be smaller than my normal force at the bottom where I feel or you feel heavier. And to prove that, we use this idea of centripetal force and centripetal acceleration. So here would be my center. All right, so at the top, I have a force of gravity. And I have a normal force. At the bottom, I have a normal force and I have a force of gravity. Okay, force of gravity in both of those spots is the same because your mass and your acceleration due to gravity are the same. It's these normal forces that change. And they have to change because you need the biggest force pointed towards the center no matter where you are in your motion. So at the top, the force of gravity has to be bigger than the normal force because if the normal force was bigger, then this object would accelerate away from the circle. Okay, but I need this force of gravity to be bigger towards the center so that I can have a net force towards the center, which would cause that centripetal acceleration. Same thing happens at the bottom. So at the bottom, now my normal force is pointed towards the center. My normal force has to be bigger than my force of gravity because if my force of gravity is bigger, I would fall away from the circle, okay? And I need that net force towards the center, which is only going to come if the force of gravity is bigger. So if I draw our free body diagram at the top versus our free body diagram at the bottom, then we have at the top, let me draw both real quick, okay? At the top, I have a normal force, which I'm gonna draw kind of small. And then I would need a force of gravity that is bigger. At the bottom, my force of gravity would be the same because I am the same person on the same planet. But instead, my force of gravity, or my normal force, sorry, would have to be bigger, okay? Now, one last thing here. When I sum my forces on something like this, I'm going to make towards the center of the circle positive. That was going to make my net force positive because my net force is always going to be towards the center. So at the top, my force of gravity is towards the center. So I would do a force of gravity minus a normal force is equal to MAC. Where at the bottom, I would do a normal force minus a force of gravity is equal to MAC. So I'm making the one towards the center positive. So here, my normal force would be my force of gravity minus MAC. And here at the bottom, my normal force would be my force of gravity plus MAC. Again, mathematically showing that this normal force would be smaller than this normal force, okay? And also notice that here, I can't just simplify my centripetal force and say that it's my force of gravity, or simplify my centripetal force and say it's the normal force, because it is the net force causing the centripetal acceleration. So really, this force of gravity minus my normal force would be my net force or my centripetal force. My net force is my centripetal force. This normal force minus the force of gravity would be my centripetal force, okay? So it can't just be simplified to the one pointed towards the center. I have to make sure that I'm looking at my net force towards the center because that's what's going to be equal to MAC, just like your net force in general was equal to MA or to 0, okay? So let me know if you have any questions. Yeah, bye, have a good day.